All right, so example number one, Giselle is 168 centimeters tall. In her high school, boys' heights are normally distributed with a mean of 174 centimeters and a standard deviation of 6 centimeters. What is the probability that the first boy Giselle meets at school tomorrow will be taller than she is? So that 168 centimeters is going to come into play. So we have here a chart that's written. We've got normally distributed, so we have it in the shape of a bell curve. This is a normal distribution where our mean is listed as 174. That comes from our question. We're also told that the standard deviation is 6 centimeters. So below our mean, 174 centimeters, I can say that my standard deviation is 6, which means it starts at 168, and of course it would also go up by 6 to 180. But lo and behold, our question is asking about 168 centimeters tall. And isn't that convenient that that happens to be one standard deviation below our mean? Okay, so we're going to be taking a look at how we can apply our concepts of the fact that our data is grouped. 68% of our data is grouped within one standard deviation of our mean. This is going to come into play. So let's start with this question, and let's just give a random variable x represent a boy's height. Because we're wondering about probabilities of finding a boy that is taller than she is. And we know that she is 168 centimeters tall, so we want to find out what's the probability that we find a boy who's greater than 168 centimeters. Well, we know, because the data is normally distributed, we know that the probability of our mean subtract one standard deviation and the probability of the mean plus one standard deviation, we know that in between those two ranges, 68% of our data falls. So 68% of the data lies in this area here. Well, because this is symmetrical, that also means that half of the data, right, this half here, must be half of that 68. So therefore, the probability that I lie one standard deviation below, so mu minus one standard deviation being less than x, that must be half of that, or 34%. And in this particular question, our mean is 174. Subtract our standard deviation of 6 means mu minus our standard deviation. 174 subtract 6 is 168. The probability, probability of being less than our mean, the probability between 168 and 174 is 34%. So this section in here, between 168 to 174, there is a 34% chance that when I find a boy, they're going to be between 168 centimeters tall and 174 centimeters tall. That represents this portion of my graph. Well, what about all the other boys that are taller? Well, because this is perfectly symmetrical, we know that this whole section up here represents half the population. Right? It's perfectly symmetrical. The whole population represents 100%. So 50% of the people must be above the mean. So the probability of x being greater than 174, finding a boy taller than 174, is 50%. So now we can say the probability of finding a boy that is greater than 168 is going to be the probability of finding a boy that's 168 up to 174, plus the probability of finding a boy that's greater than 174. And we've calculated that. We said there's a 34% chance that they're between 168 centimeters and 174 centimeters, and a 50% chance that they're greater than 174 centimeters, or in other words, is it Giselle? Giselle has an 84% chance of finding a boy taller than she is. Therefore, Giselle has an 84% chance of meeting a boy taller than she. All right. And now we want to know what's the probability that the first boy she meets will be less than 186 centimeters tall. Okay, 186, is that a significant number? I'm coming through, looking at my normal distribution, and I know that my mean is 174. 186 is above it, so I know that I go one standard deviation is 180, two standard deviations is 186. Oh, look at that. It's another special number. What we're asking here is we're talking about being within two standard deviations. And we know from the previous page that 95% of our data falls within two standard deviations of our mean. So in this particular case, again, we'll let x represent the boy's height. Let x be the boy's height. So what's the probability that the boy is less than 186? The probability that x is less than 186. So in this particular case, we know that from here down to here, right, two standard deviations. This is what we're trying to find. We know that our probability of being two standard deviations away, less than x. The mean subtract two standard deviations is less than x is less than the mean plus two standard deviations. We know that that's equal to 0.95, 95% chance of that happening. So half of that. So the top half, the probability that we're between the mean, between 174, that's our mean, to 186, that's the top half. I'll just represent that over here. So this is what we're talking about here. That's going to be half of 95%, 0.95 over 2, which is equal to 0.475. And then, of course, all the other boys that are less than 174, that's the whole rest of the curve, that's going to be 0.5. So the probability of finding a boy less than 186 centimeters is going to be the probability of finding a boy less than 174, less than the mean, plus the probability of finding the boy between 174 and 186. We know there's a 50% chance of finding a boy less than the mean and a 47.5% chance of finding a boy greater than 174 but less than 186. And so our probability becomes 0.975. So therefore, there's a 97.5% chance, 97.5% chance Giselle finds boy less than 186 centimeters. Probabilities for normally distributed data, like continuous distributions, are equal to areas under the distribution curve. However, no simple formula exists for the areas under normal distribution curves. So the simplest distribution is one with a mean of 0 and a standard deviation of 1. To convert any normal distribution to a standard distribution, we end up using our z-scores. So we're going to be looking at our z-scores next. Recall that the z-score for value of the random variable is given as this. This is our equation. The distribution of the z-scores of a normally distributed variable is a normal distribution with a mean of 0 and a standard deviation.